So we have two talks in this session, the first of which is by Aretha Teckentrup, who's the lead at Edinburgh on the ProbII hub, and she's going to be talking about physics-constrained emulators.
Right, thank you very much, Paul. So what I wanted to talk about today is really the kind of two recent research projects that we've been working on. So these are both joint work with our colleague Kostas Sigalakis, who's also part of the hub, and Antonio Vergari, and our students Jianming Bai and Christian Jimenez Beltran. Okay. So as Paul mentioned earlier today, this talk is really kind of on the topic of incorporating structure into AI methods. So in particular, this talk is going to be about incorporating some physical constraints in some machine learning type methods. Okay. So the outline of my talk is the following. So I wanted to just start with kind of a motivating example. So the methodologies apply to a much more wide range of problems, but I just wanted to show one particular example for people to have in mind. Then I'm going to talk about what we really want to do. So we're going to be using Bayesian inference in partial differential equation models. I'll explain more what that is later, but that's really what we want to do, and I'll talk a bit about the challenges that we have there, and then I'll present two approaches where you can kind of use machine learning type methods to alleviate the issues. So these are going to be based on Gaussian process emulators or neural networks. Right. So as I said, I wanted to just start with kind of one motivating application. So this is a motivating application in groundwater flow. So the modeling and simulation of groundwater flow are important in many applications. So one thing you can think of is CO2 capture and storage underground, right? So when you want to assess the risk of a potential site for the burial of CO2, you kind of have to be able to simulate the flow around the potential burial site. So a very simple mathematical model for this application looks like this. It comes from Darcy's law for an incompressible fluid. It just gives you this partial differential equation. It really just models diffusion. So what you're saying is that the water kind of diffuses through the subsurface, and the speed of the diffusion really depends on the type of rock that you have. Right? So in this case, the P is the pressure of the water, so that's the solution. The K is the hydraulic conductivity. It's the property of the rock that tells you how easily water flows through, so it essentially depends on what type of rock you have. And then the right-hand side G are sources or sink terms, so if you have water coming in or out at some points in the domain. Right. Now this, as I said, it's a very simple model, but I just wanted to show you kind of one particular equation to have in mind. You can easily extend this to multi-phase flows, so where you have gas and oil, as well as water, time-dependent flows, and so on. So in practice, in reality, the models that you have are a lot more complicated, but this is kind of a prototypical application or a prototypical model to have in mind. Okay. So one of the challenges with using this model for simulations is then if you do want it to use it for simulations, you need to know this diffusion coefficient K in the whole of the domain, right? So if you want to simulate your flow in this aquifer that we see at the bottom here, you really need to know what the conductivity value is in each of the different layers. Right? And in reality, that's just something that you don't know. So in these applications, you do have some observational data, but the data is usually very sparse. Right? So getting data is very expensive. You usually have to drill a new well to get more data. And so that's something that's very expensive, and you can't really afford to do. So the data is usually very sparse and inaccurate. You don't have that good instruments. And so you do have some information about both the conductivity K and the pressure P, but there is still significant uncertainty about what your K is. Right. So what we then want to do is we want to learn what K is. So we do want to use the data that we have, as well as expert knowledge that we have from geophysicists to infer the value of the conductivity, so that we can then use this for simulations and things like risk assessment in CO2 capture and storage underground. Typically, what people assume is that the conductivity is piecewise constant, so that's what we'll do here. Again, if you go back to the image that we have, right? So the K is really a property of the type of rock that you have, and so K will take a given value for a given type of rock. And so in that sense, it makes sense to assume that it is piecewise constant. And so we're going to denote that by theta, right? So we're back to the usual notation that the parameter that you want to infer is theta, and it's just a vector of parameters. That's just the value of the conductivity. Right. So as I said, we really want to do this in a Bayesian framework. So in this setting, we don't usually have much data, so it's really crucial to incorporate prior knowledge as well. So in this case, we then choose a prior density on the unknown conductivity theta that includes any expert knowledge. So for example, here it's natural to choose a distribution that is always positive, because it's a physical quantity that is always positive, and you can incorporate other things as well if you, for example, have an idea of the order of magnitude of the conductivity. Right. Then you use Bayes' theorem, and I think most people here are familiar with that. So you can update the prior by including data. So you condition on some observed data y. So I assume that I have this observed data y in the first bullet point here, which typically comes in the form of noisy point values of theta and or the PDE solution P. The G that appears in the likelihood, so I've written here Bayes' theorem, which I think most people have seen before, that the posterior that you get on theta is proportional to the likelihood times the prior. And in the likelihood, as in the second bullet point here, we have this map G appearing. So this is what's known as the parameter to observation map. You can really just think of it as the solution of the PDE. Right, so if you have, if your data y is data of p, you then have to kind of solve the PDE in order to compare the model output to your observed data y. Right, so in this context, the prior is really the one that incorporates the expert knowledge. The likelihood kind of makes sure that you fit your theta to the observed data, and the posterior then has a combination of both. So it's really this posterior density that you're after and that we want to compute, right? So as we said, we wanted to infer what theta is, and so this posterior, which is the conditional density of theta conditioned on the observed data y, that is then really what we're after. Right? So in practice, that is something that is very difficult to compute in these kind of applications. So algorithms that you would typically use to explore the posterior, such as MCMC or Markov chain Monte Carlo algorithms, for that you need to repeatedly evaluate the likelihood of the data. And in our case, the evaluation of the likelihood is very expensive, right? So to evaluate the likelihood, we have to solve a PDE, which is very expensive to do. And so this is just something that becomes very, very costly very quickly, right? And so something that people do is that you approximate the PDE solution. So instead of for every sample, instead of repeatedly solving the PDE for different values of theta and then looking whether that fits to your observed data, what you do is you approximate the PDE solution. So you approximate G by something that's cheaper. So I would usually call that a surrogate model. What you call it depends a bit on what community you're from. So some people call it emulators or reduced order models or meta models. It's really just an application. It's really just an approximation or a simpler model. So you can really just think of it as an approximation to your PDE solution that is simpler and cheaper to compute. Right? So you could think of it really as just a numerical solver, so your standard finite element or finite difference methods just on a very coarse grid, right? Again, that's very cheap to do, or something like neural networks or something like that, right? So it can really be pretty much anything that you like. Okay. So that's then what people use. That does solve the problem that you can do the computations, right? So then you have something that you can actually perform inference on. But you have made an approximation, and so if you're then going to use the value of theta that you infer to do another task later on, you do have to think a bit about the error that you're introducing with that approximation, right? So you're not using the true model anymore. You're not really using the PDE. You are using an approximation for the inference. Is that inference still valid, right? So you do have to think about whether you get something that's accurate. Okay. So in the kind of straightforward setting, or the kind of the first thing that you could think of doing, it actually turns out that this is most of the time not a very good idea. So if you really just take the surrogate model for the PDE solution and then plug that into the posterior distribution instead of the PDE, that usually gives you very bad results, right? So it gives you biased and overconfident predictions, right? So for that, I want you to look at the top graph here. So here I've plotted the posterior distribution that we're after on a two-dimensional vector theta. Right now we have two constants, theta1 and theta2, that we want to infer. The true value of theta1 and theta2 is marked by the little black cross. I hope you can see that. It's at the bottom of the blue contour. That is the kind of true value that generated the data. So we're using synthetic data here. The blue contour is the true posterior, which means it's the posterior computed with the actual PDE solution, or a reference solution computed with a very fine mesh. You can really view it as the true PDE solution. So that's really the reference. That's the thing that we really are after, right? So that's the truth. Okay. What we've done for the dark orange contour is really just approximated the PDE solution by a surrogate model and then plugged that into the posterior and then done our inference, right? And you can see that it is biased, so it's really shifted and it's really concentrated on the wrong part of the parameter space, but it is very confident, right? It's not very broad. It has a very small variance. It does focus on a very narrow range in the parameter space. If you look at it, you might think that you're doing well, right? You think, I'm really confident, I've really narrowed down where my true parameter is, so this is really good, but it is actually in completely the wrong space, the really wrong part of the parameter space, right? So that's something that you really need to be aware of and that you would possibly want to avoid if possible. Right. So what you want is that you have surrogate models that are uncertainty aware. Right? So when you construct your surrogate model, you really want to have some uncertainty quantification in the model so that it knows that it is wrong, right? So in a way, for the dark orange bit, you're kind of taking the model, you know it's wrong, but you're pretending it's right, and that's really where it goes wrong. And so you really want to plug in the wrong model, but be aware that it is the wrong model and kind of incorporate that extra uncertainty that you get into your inference, right? And that's really what we're doing in the light orange line in the top plot. That is where we really have a surrogate model that is uncertainty aware, so it does know that it's incorrect, and it kind of has an uncertainty quantification around it, and that's where you then get this more spread out light orange plot, and you can see that that does have a lot bigger overlap with the true posterior, and in particular it doesn't give kind of zero mass to the true value anymore, right? So this is really something that then allows you to at least acknowledge that your inference is not as good as you think it is, right? So you do want the uncertainty-aware surrogate models. The other thing that you ideally want is to really incorporate the fact that you are solving a partial differential equation, right? So in this case, we actually know what the true model is. We know that it is the partial differential equation. We just can't go and solve it all the time because it's too expensive, but we do have some knowledge about what it is. And so you really do want to incorporate that as well. And what that does is really improve the accuracy, right? So that's the bottom plot where the interpretation of everything is kind of the same. So the cross is the true value that generated the data. The blue contours are the true posterior with the true PDE, And then the green plots are the ones with the surrogate model, the one that's uncertainty aware and not uncertainty aware. But this time we have enforced the PDE constraints, so we have included this in the construction, and you can see that it does really significantly improve the inference there as well, right? So these two things really solve the two different issues. So the uncertainty aware solves the problem that you're overconfident, right? So it's kind of getting you back to the right level of confidence that you should have in your inference. And the PDE one is the one that kind of gets rid of the bias and it improves the accuracy. Right. So I'm now going to quite quickly show you two ways that we have of doing this. So we've looked at two ways of constructing these surrogate models that give you the uncertainty quantification and give you the PDE constraints as well. Okay. So the first construction is based on Gaussian process surrogate models. So this has been mentioned many times before today as well, and I think many people are familiar with it. If you're not familiar with it, I don't think you're going to understand it from these slides, so I'm going to be relatively quick. In these Gaussian process surrogate models, it's really a Bayesian methodology to construct the surrogate model. So to construct the surrogate model of our PDE solution G, what we do is we first put a Gaussian process prior on it, and then we condition it on some function values to get the posterior, right? So you start with a prior, such as in the left two plots on your unknown function, right? So you view the PDE solution as a function, in this case of the unknown parameter theta. And then you put a prior on that function, so that would look something like the samples in the left-hand plot here. And then what you do is you actually evaluate the function at some input, so that gives you these black dots there, and then that updates to a posterior using Bayes' theorem again, and so that's how you get the uncertainty quantification in the surrogate model, right? Because it is a Bayesian posterior, it does automatically give you this uncertainty quantification. So if you do want to include the PDE constraints, you can do that as well. So incorporating linear constraints is relatively straightforward, right? So you just use that when you apply a linear operator to a Gaussian process, you still get something that's Gaussian. Nonlinear constraints and nonlinear PDEs are a lot more difficult, but there is some work on that as well. So if you do want to incorporate a linear PDE, such as the equation that I showed you on the first slide, so the Darcy flow equation, you can write it in terms of this linear operator L, right? So I've just now denoted the left-hand side of the PDE by this operator, differential operator L of theta. Okay. So again, this is going to be quite fast, but I just wanted to show you some of the maths that's involved. So to then incorporate this PDE constraint in the inference, what we do is we put a Gaussian process prior on the PDE solution P, as well as the right-hand side G jointly, right? So the G was just the right-hand side in the PDE, so it's on the first line there. So we're solving L, P is G. So you can put a joint prior on P and G, and because P and G are related through the PDE, that's how you get the PDE operator into the Gaussian process, right? So the PDE operator L, you can see then appears in the covariance structure, and that's really how you get it in. And that's how you can then do this inference, and that's how you get the improved inference that I showed you on the right-hand side here, right? You can do something that's a bit cheaper and kind of in between the two things that in the middle plot, but I'm not going to be talking about that now. Okay. Then again, a bit quickly, so we also have some work on using neural networks for these uncertainty-aware and PDE-constrained surrogate models. So we're basing our approach on this deep Galerkin method. So that was proposed by Sirignana and Spiliopoulos in 2018. So this is now a method that provides a neural network that really approximates the PDE solution. right? So it takes as an input both the spatial variable x and the parameter value theta, and then the neural network, so the FW, where the W denotes the weights of the neural network, that is then trained so that you approximate the PDE solution as a function of x and the coefficient value theta. Okay. So the way that most neural networks with PDE constraints work is that you change the loss, right? So the way that you incorporate the PDE here is in the loss function. The loss function looks something like this. So what you do is you sample some points. So in the first bullet point here, we're sampling these points xi, dxi, and theta I. Right, so we're sampling different parameter values of theta I, so we're training it with different values of the parameters. And then we're choosing some points xi, which are in the interior of the spatial domain, and then some points dxi, which are on the boundary. And then in the loss, what we do is we have these two terms. The first one, which should be Lg, so in the third bullet point, the LH should be Lg. And that's kind of the one that measures the error in the differential operator, right? So we have a term that's really just looking at the residual in the PDE. So at this point, xi and theta I, am I satisfying the PDE? So if that term is 0, you are satisfying it exactly. And the second one, so the last bullet point here, that's kind of enforcing that you satisfy the boundary conditions as well, right? So that's why we sample different points in the interior where we enforce the PDE, and then on the boundary where we enforce the boundary conditions that we have. Okay. So that is the original method, which already gives you the PDE constraint. So our contribution was to provide the uncertainty quantification. So what we do there is we kind of develop a Bayesian version of this deep Galerkin method. So to do that, we interpret the loss as a negative log likelihood. By doing that, the likelihood that you get then kind of characterizes how well the weights or the neural network that you get with the certain weights W approximate the PDE solution, and that then gives you a posterior on the weights as well. Okay. To kind of keep the computational cost down, so we've heard that many times as well today, that once you start doing Bayesian neural networks, things can get very, very expensive. And so to keep the computational cost down, we only randomize the weights in the final layer, so the weights in all of the other layers are fixed, and we do a Laplace approximation on the of the posterior. And both of these things have been studied, and it's generally, for a lot of tasks, considered that this is good enough to deliver good uncertainty estimates. And if you want references for that statement, that is in our preprint. Okay. So just to show you then one figure of how this works. Yeah. Here we've actually trained it on Berger's equation. And you can see that, so the main point I wanted to show you was the uncertainty estimates. So the red lines here are the uncertainty estimates that we have. And you can see that we do actually get good uncertainty estimates in the sense that the true solution is actually within our uncertainty bounds. I don't think I have that much time to talk about the figure. So I'll just quickly move on to these conclusions. So I just wanted to stress again that, we're looking at partial differential equation models which appear in very many areas. If you then want to do downstream tasks like parameter inference for these kind of models, that can become very, very expensive. A common alleviation is to use surrogate models, but if you want to do things in a way that are kind of still tractable and accurate, and kind of to avoid these overconfident and biased predictions, you really have to think about surrogate models that come with uncertainty quantification and that incorporate the physical constraints. And I'll just leave these references up here, and thank you very much.
Okay, we have time for a couple of questions.
Thanks. Could you go down to slide 11? Yeah, Tiny, some questions. Generally good enough, is that empirical or is there a theoretical result?
So they compared it to, I think, Markov-Chain Monte Carlo sampling. So kind of so they've chosen some reference which they know is accurate, and then they've compared it to that.
Okay,
yeah.
Thanks. And small question about slide 10 as well. The loss in there, I was surprised to see that the two loss terms are not, like that you don't have some hyperparameter balancing one or the other. Is it not important because both of them will go to zero and you feel confident about that? Or, yeah.
Yeah. I don't know. So I think this is what they use in the original method. I'm not sure if they tried using different weights, but I don't see why you wouldn't be able to use different weights as well.
Thanks for a great talk. How do you put a prior on neural network weights? What do you use?
So I think we just use a Gaussian. So we just put IID Gaussian weights, zero mean, and I don't remember what variance.
So do you think that matters? Will that not affect your results?
It does matter. So I think one of the reasons that we use it as well is because of the Laplace approximation. So for the Laplace approximation, you have to compute the Hessian of the negative log likelihood. And so with the Gaussian weights, that's an easy term that you can compute. So it does simplify that. So that might come in as well. But I'm not too familiar with what other priors people have tried.
Yeah, so maybe one last question.
Thank you for the great talk. I was wondering if you could speak a bit about the neural network architecture that you use. Like, have you tried like the UNets or Fourier neural operators? Like, what have you found to be effective, and is it really sensitive to it?
Yeah, so I think this method generally works with any architecture. We just chose a very simple one. So I think all the results that I showed is just a simple feed-forward neural network.
Okay, so if there are any more questions, I suggest you just try and ask them or Aretha after the session, and let's thank her again.
Thank you.